Okay, good morning. So we have done in the last class some minimization of the norm, basically the projection theorem. So let me just recall that projection theorem. Yeah, this is the projection theorem. Yeah, this is the projection theorem here. Norm of x given a compact closed convex set subset of a Hilbert space, then any point there is a minimum point in K. So this is the theorem which we have done here. Okay, and now we will use that to prove some general abstract theorems. So basically proving 2 or 3 abstract theorems for the. Okay. So let me try to do some results now based on that. So we will start theorem. This is theorem of what is called a variational inequality. Variational inequality. Okay. First we will prove the case when A is symmetric, and then because symmetry case is essentially the previous minimization problem, but it is not symmetric, it is something different. So let A from H to H is a Hilbert space, be a symmetric elliptic, so all the thing elliptic or cohesive and continuous bilinear form, continuous bilinear form, and K be a closed convex subset of H, subset of H. Then let F is in H. Of course, F will be able to take in H prime also, but in PDEs that is important, but as such we do not require here because H prime can be identified with H, but when you study PDE and PDE problems you see a difference of it. Then there exists unique U in K such that A of U V minus U greater than or equal to F V minus U. This is the variational inequality. This is called the variant. Further, U can be characterized by a minimization problem by find U in K and JU equal to minimum of JV over V in K. So it is a minimization problem where your JV is equal to half of AVV minus FV. FV is the inner product. If F is in H, if you treat F is in H prime, then it is a duality bracket. That's so the proof is actually, so let me give you the proof quickly. Proof is, this is basically, this problem can be converted into a problem of the minimization of the norm, which we have done the previous thing by redefining the norm. So the redefining the inner product because A is a symmetric form, A, the first note A defines a new inner product, new inner product on H, H as denoted by norm UV, inner product UV is equal to A u v. So, verify this, you can verify. You need symmetry, that is what you have. And the further this is equivalent to, this is also verify, this is equivalent to the standard inner product, to the given inner product on H, to the given inner product on H. That is what you have to do, verify. This also verify. Okay. So, this defines an norm also, right. So, the norm of u we denote by to its inner product with that is nothing but your AUU power half. So, it is an equivalent inner product. So, and immediately you can see the following. Okay. Now, these are the two things. Look at this functional, look at v going to f of v. This is a linear continuous functional on H. Since the norm A is equivalent to the given norm, this is also linear and continuous, is linear and continuous with respect to the new norm also. You know that this is linear and continuous with respect to the given norm, this is also linear and continuous with respect to this norm. Therefore, by Rees representation theorem, so apply Rees representation theorem with respect to the new norm, there exists f tilde in H such that f v can be represented as f tilde v. You will get f equal to f tilde of v with respect to new inner product. Keep that in mind. Okay. With respect to f tilde v, that is equal to a of f tilde v. Okay. So, here is a small exercise for you immediately. Prove that now your JV is equal to half of norm of V minus f tilde with respect to this norm square and minus half of this, just a computation f tilde with respect to this norm. Okay. Square. We just compute that. Okay. So, what this shows that, look at it. So, this is a constant, this is a constant. So, minimizing JV is equivalent to minimizing this one. This is precisely your minimization problem. So, the minimization, the minimal value may change, but the minimizer will not change. Which minimizes? Because once you are minimizing certain things by adding a constant, the minimizer will not change at all. So, you can minimize this. Okay. So, that is it. Then you apply the previous theorem. Okay. So, apply previous theorem. So, with that remarked, so the minimizing JV over K is equivalent to minimize norm of V minus f tilde over A. Okay. So, that is it. So, then this is essentially the first theorem we have proved. This is the first theorem we proved. Apply it to get the result. Apply it to get the result apply it to get the result whatever you want. This is what you get it, f tilde of u v minus u with respect to a less than or equal to 0, which gives the required result. Required, rewrite it, required theorem. Okay, that's it. All right. Now we are the condition of symmetry, it gives you the inner product, A defines an inner product, but then the variational inequality is also true without the symmetry assumption on A. This is the theorem due to Stambakia, but of course you do not get a minimization problem in that case. So you only get the variational inequality, and the trivial proof which we have given using is essentially applying Riesz representation theorem and redefining the inner product. That proof will not work. So let me try to give a proof of that theorem. So theorem Stambakia. Okay. So let A be continuous, elliptic, no symmetry assumption, bilinear form on H. Okay. And F is in H, then there exists unique U in K, and of course your K is there, and K subset of H closed convex. This we are always assuming convex such that A of U V minus U greater than or equal to F V minus U for all V in K. Okay. So this is a similar theorem which we have proved. So you see you have this thing here. Okay. All right. So let me give a proof to require some extent. So let me go to the next page. So we will give a proof. So proof. So let me do it in two so that you can read this one. So let U belongs to H be fixed. Let U belongs to H be fixed. And then V going to AUV is linear, continuous, and all that is linear, continuous. So that implies by applying that result is every linear function can be written as an inner product for an element. So there is an element implies there is an element in H. That element you call it ALU. So there exists AU, we denote this AU. There an element exists, that element depends on U, so we call it. There is an element H such that AUV is equal to AU V for all V in H. This is just a Riesz representation theorem. So that means there is a mapping A from H to H. So the linear bilinear functional gives a linear operator, continuous linear operator. So it's a simple exercise. You should work out this exercise. A is also linear, which needs a proof. Initially it's given A is also linear and continuous, and by ellipticity, so these are all part of exercise, and norm of AU, this is continuity less than or equal to the same M into AU, because the continuity estimate of AU, and then AUU, this is a small AUU, this is greater than or equal to alpha into norm u square. These are all you can immediately prove it as an exercise. So it's almost trivial, but make sure that if you are learning this topic, make sure that it is there. Therefore, what is our problem? So we have to prove that we have to prove this, right? Prove that AU V minus U is greater than or equal to F V minus U. This is what you want to prove it. So this is equivalent to proving, I am not yet, but it is an equivalent to proving AU V minus U. So the AU, so AU V minus U is equal to capital AU V minus U. So I take F here, V minus U, bringing is greater than or equal to 0. Okay, this is equivalent. So I may not write all the time. So we are going to, what we are going to do is that basically our inequality problem, we are going to convert it into a fixed point problem. Okay, this is true for all V in H. So you have to find U in K, this one. So you have to find U in K such that for all V in V for all V in K. And did I mention, what did I mention here? V in K. So let me check what I have done here. Yeah, it's correctly written. So I will do a small trick. So choose row positive. Okay. Then this is equivalent to, this is a slight small trick which you will be doing in analysis all the time, row of AU minus row of F V minus U greater than or equal to 0. Now this is I am going to write a projection inequality. So I will add, this is add and subtract minus row of F. So okay, row of F plus U minus U V minus U greater than or equal to 0. So I will write it as a less than or equal to inequality, that is you always write for a projection inequality. So I will write row of F. So I will write row of F minus row of AU plus U minus U V minus U is less than or equal to 0. These are all for V. Now look at this one. This inequality, the above inequality is true. This is precisely the projection inequality we have proved. The above inequality is what you want to prove is true if this one, the if pk of this one, this portion is a projection of U. You look at it. So that means pk of U should be the projection. That is what the projection inequality, row of F minus row of AU plus U is equal to U. That is what you want. You want that to the projection of U, right, that one. So this, so we define a map F from H to H by F of V is equal to pk of the projection row of F minus row of AU plus V rho AV plus V. So, you define that, okay. Rho of F minus rho of AV. So, so therefore, inequality is true, inequality is true if and only if F has a fixed point, F has a unique fixed point. Okay. So, all right. So, we can actually show that. So, you want to show F is a contraction. So, I will so the 2 steps I will do this one. So, first you derive F of V1, this we have answered, this it is a projection. So, the F is a projection. So, the projection decreases the distance. FV2 is less than or equal to, you can just verify this one, norm of V1 minus V2. So, let me write down as a minus, F will get cancelled and A into V1 minus V2. This we have done. Pk of x1 minus Pk of x2 is less than or equal to norm of x1 minus x2 V2. Okay. So, so you do that one. So, you square it and expand it, f of V1 minus f of V2 square. So, you do this computation and then I will write an inequality. This is less than or equal to 1 minus 2 rho alpha, apply these inequalities, plus rho square m square into norm of V1 minus V2 square. Expand it and do this one. So, what we need is here, so we need this to be less than 1. We require this to be less than 1. So, let me write it separately in the next page. Okay. So, we need, for that inequality to be true, we need 1 minus rho 2 rho alpha plus rho square m square should be less than 1. This is what our question. So, so choose 0 less than rho to get the above inequality. This is if and only this is true if, let me not write if, this is true if choose rho less than 2 alpha by m square. Okay. So, once you choose this one, this will imply this one, that will imply f is a contraction. Okay. F is a contraction and you get a fixed point and you will get the Stumpakia theorem, that implies Stumpakia is an inequality. Okay. Now, a simple corollary, if k equal to m, k equal to v is a subspace, subspaces are a closed subspace, subspace closed contained in H. Okay. And subspaces are always convex. So, there is no need to verify, all the subspaces are much more than convexity. The entire line is there. Convexity means only between 2 elements are there. Okay. So, you have a convexity. So, you have a u v minus u greater than or equal to f v minus u. So, because of the subspace u and v are in V, for u is in V and this is for all V in V. So, I can choose V equal to arbitrarily. So, I can replace now, I can take a replace V by V plus u, because V is in u, V is in V, u is in V, V plus u is also in V, V in V by V plus u in the inequality, because it is arbitrary. So, I can replace V by V plus u in V. That will imply you will get your A. I use the same notation, the replaced one, V replaced by V plus u. So, you get your AUV greater than or equal to FV for all V in V. Okay. And now again it is a subspace, now replace V by minus V, that will imply AUV less than or equal to FV. In other words, you get equality, implies equality AUV equal to FV for all V in V, and you are looking for solution U in V. Okay. So, in particular if you take V equal to H, in particular a special case, particular take V equal to H and you get your what we call it the famous Lax-Milgram lemma. Milgram lemma. Let H be H A be as above, B H A means the bilinear form, B as above, F is in H, then there exists a unique U in H such that AUV is equal to the equality problem. So, these are called unconstrained minimization. If it is a symmetric, it will become characterized by a minimization problem. So, when you have a minimization with constraint, you will get inequality. When you get a minimization without constraint, it will lead to equality. So, okay. So, the constrained minimization problem leads to inequalities, unconstrained problem leads to equality H. So, you can solve this problem. So, it is a very nice problem, you can do it. Further, if A is symmetric, this is any without any assumption, if A is symmetric, U is characterized by Ju equal to U in H, Ju is equal to minimum of Jv, okay, where V in H, and Jv is equal to half of AVV minus FV. Okay. So, you can do that. So, that is a famous, and we are going to see the application of this thing in thing. So, let me state one more important theorem, and I will prove that theorem. I will explain it in the next class, but let me at least state so that we can straight away go to the proof. This is called the famous Babuska-Bressy theorem. See, in application you will see more when you study even evolution equation. In applications you may come across, we may see abstract problems, abstract problem in the form of operators. Already you are seeing abstract problem, but you can also represent instead of the variational structure you can do in terms of the abstract operator form. Okay, abstract operator form, something like du by dt equal to au, which we will see it in the evolution situation. But for systems, this is systems, also you will see in the elliptic form something like au plus b star of u equal to f or k, something else, and b of u. We will see examples. So these are all motivated from examples. Okay, and b of u is equal to L. This may be in some Hilbert space and this will be in another Hilbert space, etc. So Babuska-Bressy theorem gives conditions under which the system of equations, especially many systems, we may see at least a couple of things we will see later. So let me just state the Babuska, or maybe Babuska-Bressy theorem. So maybe I will stop here and then continue in the next class. It is already time for a class. So we will state this theorem and try to give a proof of it, and the proof is based on what is called a Fredholm alternative. So it is an operator equations. I will try to almost sketch, so but we will be using the Fredholm alternative. So it is a good time to recall and study what this Fredholm alternative is all about. Thank you. Thank you.